Hello dear children, Mrs. Naziya Ustad from St. Joseph's High School is here with part 4 of the chapter Motion. In this video, we are going to discuss graphical representation of motion, derivation of equations of motion, and uniform circular motion. Graphical representation makes it simpler to understand the data. When analyzing motion, graphs representing values of various parameters of motion make it simpler to solve problems. Usually, we use line graphs to describe motion of an object. First, let's look what the distance time graph is. A distance time graph gives a variation of distance covered by an object with the time. Through this graph, we can understand whether an object is moving with constant speed or variable speed. In the graph, time is taken along x-axis and distance is taken along y-axis. Let's interpret some distance time graph shown here. This is a distance time graph for an object at rest. It means the object has not covered any distance for a particular time, or it is remaining at the same distance for a particular time period. So, a distance time graph for an object at rest will be a straight line parallel to x-axis. The distance time graph for an object in uniform motion is always a straight line because in uniform motion the object covers equal amount of distance at equal intervals of time, while the graph for a non-uniform motion is a curved one. As described in the distance time graph, velocity time graph shows variation of velocity of an object with the time. In this graph also, time is taken in the x-axis and velocity is taken in the y-axis. The slope of the graph will give you the value of acceleration. Let us recall that slope is the difference in y-coordinates divided by difference in the x-coordinates for a given particular coordinates of x and y. Here the y-coordinates are difference in the velocity, that is v2 minus v1, and x-coordinates will be for time t2 minus t1. Whenever there is a change in velocity, we should know that we are talking about acceleration. So, the slope of velocity time graph gives acceleration. How will you get displacement from the graph? In order to find the displacement covered between two time intervals, the area of that graph or the area under that portion of the graph is taken to find the displacement. Let's interpret some of these velocity time graphs shown here. The first one is a graph for an object moving with constant speed or uniform velocity with zero acceleration. Such a graph is a line parallel to x-axis. For a uniform acceleration or uniformly accelerated motion, the graph is a straight line either starting from the origin if initially the body is at rest, or starting from any point in the y-axis if the initial velocity is not zero. For uniform retardation, the graph starts from the y-axis and ends in x-axis. Dear children, in this video, we are going to derive equations of motion by graphical method. We use velocity time graph to derive equations of motion. Here, we are drawing the graph for an object moving with uniform acceleration. The nature of graph for uniform acceleration of an object is always a straight line like this. You could ask me that why didn't we draw the straight line from the origin O? Why we are taking the line above O? Let me tell you children that if you take the motion of the object from O, then the initial velocity of the object becomes 0. And if you take the initial velocity as 0 in the equation of motion, then we don't get the required equation. As the first equation of motion is v is equal to u plus at, in which u is the initial velocity. If we take u is equal to 0, then the equation becomes v is equal to 0 plus at, which means v is equal to 80. If we take the graph from O, then we get v is equal to 80, which is not the actual equation. Now consider an object moving from point A to point B with uniform acceleration. Now let us draw a line BE perpendicular to x-axis. The coordinate of B on x-axis is time t. Now draw a line BC perpendicular to y-axis. The coordinate of B on y-axis is velocity, that is final velocity v. The initial velocity of the object at point A is u and v is the final velocity of the object at point B. Now draw AD parallel to x-axis. With all these arrangements, let us start the derivation of the first equation. Here you can see that the line BE is the sum of BD and DE. That is, BE is equal to BD plus DE. And this can be written as BD is equal to BE minus DE. According to the graph, BE is equal to V. If we substitute the value of BE in the above equation, we will get BD is equal to V minus DE. And substitute DE is equal to U as well. Because DE is equal to OA, which is equal to U. Hence we get BD is equal to V minus U. Let's consider it as an equation number 1. As we know that acceleration is given by the change in velocity divided by change in time. From the graph, change in velocity is BD in time t. Therefore, A is equal to BD upon t. Now from equation 1, we have BD is equal to V minus U. Let us substitute the value of BD as V minus U in above equation. We get A is equal to V minus U upon t. If we transpose t on the other side of the equation, we get AT is equal to V minus U. And now transpose U on the other side, we get at AT plus U is equal to V. If we rearrange this equation, then we get V is equal to U plus AT, which is the first equation of motion. Here, V is the final velocity, U is the initial velocity, A is the acceleration, and T is the time taken. Hence, the proof. Now, let us derive second equation of motion. Here we have a velocity time graph. As we know that area below the velocity time graph gives us distance. In this graph, the complete yellow colored area gives us distance. Let us divide this complete area into two parts as triangle BDA and rectangle AOED. Now distance is equal to area of triangle BDA plus area of rectangle AOED. We know that area of triangle is half into base into height and area of rectangle is length into breadth. In graph, the base of the triangle is AD and height is BD. And in rectangle AOED, length is OE and breadth is AO. If you look at the graph, AD and OE are parallel to each other, which means they are equal. So here OE is equal to time T and BD is equal to AC. And also OA is equal to U. Now we got half into T into AC plus T into U. Now how can we replace AC? Now let's look at the graph. If we subtract OA from OC, we get AC, which means AC is equal to OC minus AO. Here OC is V and AO is U. Therefore AC is equal to V minus U. Let's substitute this value here. Distance is denoted by S. Therefore, S is equal to half into T into V minus U plus UT. We know that V is equal to U plus AT. If we rearrange this equation, we get V minus U is equal to AT. If we substitute this value of V minus U in the above equation, we will get S is equal to half into T into AT plus UT. Now let's simplify this. S is equal to half into T is T square, then it becomes half into AT square plus UT. And when we rearrange it, we get S is equal to UT plus half AT square, where S is distance, U is initial velocity, T is time and A is acceleration. Hence the proof. Now let's derive third equation of motion. Let's consider the same graph here in which area below the graph gives us distance. Let's tilt the graph like this. Here you can see that the area under the graph looks like a trapezium. Area of trapezium is given by half into sum of parallel sides into height. In this trapezium, the parallel sides are BE and AO into the height is AD. Here AD and OE are parallel. Thus OE can be taken as time T. Here BE is equal to OC, which is equal to V, and OA is equal to U. So this equation becomes half into V plus U into T. We have V is equal to U plus AT, first equation of motion. If we transpose U on LHS, it becomes minus U. And also, if we transpose A on LHS, which is in multiplication with the T, here gets into division on LHS. We get T is equal to V minus U upon A. Let's substitute the value of T in S is equal to half into V plus U into T. It becomes S is equal to half into V plus U into V minus U upon A. Here we notice that A is under multiplication with the 2. So the equation becomes S is equal to V plus U into V minus U upon 2A. We know an identity A plus B into A minus B is equal to A square minus B square. So here V plus U into V minus U can be written as V square minus U square upon 2A. Now if we transpose 2A on LHS, it is multiplied with S here. Therefore we get 2AS is equal to V square minus U square. After rearranging, we get V square minus U square is equal to 2AS, which is the third equation of motion, where V is final velocity, U is initial velocity, A is acceleration and S is the distance. Uniform circular motion. Uniform circular motion describes the motion of a body traversing a circular path at constant speed. The distance of the body from the axis of rotation remains constant at all times. As an object moves in a circle, it is constantly changing its direction. Merry-go-round is an example of uniform circular motion. Satellites orbiting our Earth, artificial satellites, or our moon has motions that are very nearly uniform circular motion. The planets that orbit our sun has motions that are very nearly uniform circular. Dear children, here we completed this chapter. I hope the concepts will be clear to you with these videos. Thank you.